Hi, in this lesson, I want us to take the ideas we learnt last time about how rocks cool and move them on a step. But to do that, I want us to go back to this particular rock that I showed you in the last lesson. And the question I asked was, how did this rock actually cool? Now, when we look at this initially, we can see that it's porphyritic. We've got some large crystals, large phenocrysts these are actually a feldspar, surrounded by a ground mass of finer grained minerals, which includes minerals like mica, quartz, more feldspar, probably maybe even a little bit of augite in there as well. So far, so good. Except if we actually look carefully at the scale that's given for this rock, we can see that that scale bar at the bottom is 25 centimetres. These phenocrysts are maybe 30 centimetres long. The ground mass here, the crystals in that, maybe a centimetre across. This rock is incredibly coarse. The crystals in it are enormous. Now that does starts to think about, okay, how did this rock cool? Well, clearly extremely slowly, and in two stages. But I want us to move on to start to think about, well, if that's the case, where did that happen? Something to ponder for today's lesson. This is a photograph of a cliff. We've got some red sandstone there, but then we've got this odd slab of basalt, an igneous rock within the red sandstone. So what's actually happened here? We're going to come back to this photograph at the end, see if you're able at that point to explain what's going on here. We're working today on pages 7 and 8 of our Theme 5 booklets. Let's go. When we start thinking about where igneous rocks cool, there's some language that we need to get to grips with. We need to understand what each of these terms means. Each of these words are on your specification, and each of them could appear in the exam. Now, some of these you may be familiar with already, but what I want to do is I want to go through and explain what each of these terms are. And what I'd like you to do is I'd like you to add some annotation to the diagram on page 7. Okay then, let's start with some of the igneous features here. The first one I want to consider is a pluton. A pluton is a crystallized magma chamber. It's a very large body of igneous rock that crystallizes beneath the surface. Coming off that pluton then, you can see long, thin, sheet-like bodies of igneous rock cutting across the beds that are there. Where we have this sheet of igneous rock cutting across the surrounding rock, we call that a dike. Where we have those sheets of igneous rock then that follow the layers within the surrounding rock, that then is a sill. So we've got these three terms now for the igneous rocks that crystallize beneath the surface. We call these igneous intrusions because they intrude into the surrounding rock. Now that surrounding rock geologists give a very general name to. We call that the country rock. And that can apply to any type of rock that's around one of these igneous intrusions. It could be sedimentary, it could be igneous, it could be metamorphic, doesn't matter. It's a very general term, we call it the country rock. Now sometimes fragments of that country rock fall into the magma and they form a feature we call a xenolith. Xenolith is a word that means foreign rock. So it looks different from the rock, the igneous rock that we find it in. It may have been sort of heated up and partly molten even, but it's different from the rock that we find it in. Where we get igneous rocks making their way to the surface, we can have magma erupting onto the Earth's surface to create lava or a lava flow. So lava is just molten rock at the surface. And there are times when that magma erupts, it perhaps doesn't go very far away from the volcanic neck, which is where it reaches the surface, and will build up a volcanic cone. It's worth bearing in mind that volcanic cones are built up by the volcano. It's not that a volcano will erupt from a cone-shaped mountain. As you can see on this diagram, there are other terms that go along with these igneous rocks, but we don't need to worry about those. It's just the words that are on that list that are important. Make sure you've got some good notes so you know what each of these means. You may even want to Google them to get a nice tight definition of each of them. Okay. Once we've done that, you'll see that there are 3 boxes on your diagram. What I'd like you to do there is to think about which type of rocks might be found in each of these places. Think about the link between where these rocks cool and how quickly they'll cool. Where are we going to find the coarser rocks? Where are we going to find the finer grained rocks? So you should fill each of those boxes with the name of either one or more igneous rocks that might form there. Press pause now and have a go at that. Okay then, let's see what you've come up with. So on our diagram, on the lava flow, we're going to find the finer grained rocks, either basalt or andesite, depending on the composition of the magma that's coming out of the volcano. You know, how much silica there is in it. In a dike or a sill, there's more chance of it being dolerite. It'll cool more slowly because that magma will be insulated by the country rock. It is possible to find basalt or andesite dikes and sills if they're very small. So if they're quite thin, they'll cool quite quickly. Finally then, our pluton will be made of coarser grained rocks like granite, maybe gabbro. Okay, now we've got the link between the rocks and the size of their crystals and where these things cool. We can go back to this photograph. What do you think has happened here? What are we actually looking at? What type of feature is this? The answer to this is that what you're looking at is a small dike. The basalt here has been injected as a magma into a crack in the red sandstone. You can see that the basalt is forming a sheet or a slab of igneous rock, and you can see that basalt is cutting across the layers within the red sandstone. So this feature we can identify as a dike. We also know that that basalt must be younger than the red sandstone, because that red sandstone had to be there for the basalt to be injected through it. Okay, we started this video by looking at a rock from Land's End. I thought we'd finish with a sunset over Land's End. What I'd like you to do now is have a go at the questions on page 8 of your booklet. Can you identify the features we've just been talking about? Write in your identifications and we'll talk about them in the next lesson. I'll see you then.